Good morning, students. Welcome to the next lecture. In the previous lecture, we were discussing about the dual nature, in which we saw it that the scientists proved it that they are the electromagnetic radiations. The second part of it, that is, in the dual nature, we wanted to prove that it's also a particle nature. So, for any radiations, dual nature, we want to prove it today that particles, they are the particles. We want to prove it. Now, for it, we are having it as actually a first time Max Planck was a scientist who studied it related to these particles. He first time told it that whatever the radiations are there, they are having it as a particle nature. The reason is he wanted to explain it that these components are having some energy. If these compounds are having energy, that means we know it that energy can neither be created nor be destroyed. It can be simply transferred from one form to the another. So that means when these radiations are reaching to some surfaces, they are absorbed by the surface. So at that time, some energy transfer would have been taking place. So that means they are converted either into some particles. Mass is there, certain energy is there. So Max Planck proved it that energy for it, it's having it as an E is equals to h nu. Max Planck was the first time he proved that it's having it as an energy, which he compared it with a wavelength. Actually, he gave out the equation as E is proportional to frequency h. It's a Planck's constant, proportionality constant. Its value is 6.626 into 10 raised to minus 34 joule. This was the first time Max Planck proved it. But later on, it was being the certain postulates he wanted to deal with it. So he told that the first factor, the surface which absorbs, or the one which emits, the all types of energies, radiations, the surface which absorbs or emits all the types of radiations having different frequency. That means this is a radiation, means wave nature, frequency. We told it, yeah, in our previous lecture we told it that frequency, that was for the wave nature, right? Now here the wave we want to convert it into particle also. So the surface which absorbs or emit all the type of radiations having different frequency are called as black bodies. And those radiations emitted by it they are known as black body radiations. So this was the this was the first factor the Planck told it. The second factor, except the black body radiations, the second factor he told it that these energies which are absorbed or emitted are also termed as photoelectric effect. The second point he wanted to prove it, that was related to the photoelectric effect. Now what is the meaning of the photoelectric effect? Now to explain this photoelectric effect, the Planck was being helpful by the another scientist. Now this photoelectric effect was explained by Hertz. The Planck was helped by Hertz. Now Hertz did an experiment. In his experiment, he told that the electrons which are ejected from the metal surface, when the electrons are ejected from the metal surface, as soon as the beam of light falls on that surface is known as photoelectric effect. That means, just a moment ago the Planck was saying it, when anything falls onto the surface, they are being absorbed or emitted. The energy which is emitted, here it's an experiment, the energy is emitted in the form of electrons, and we know it that electron consists mass, and the component which has a mass, they are known as particles. So the Planck and Hertz together proved it that whichever the radiations are having, these radiations are also having particle nature, because radiations falls onto the metal emits the electrons are having mass, so whatever the radiations are there, they are having mass. So Hertz proved it that the electrons which are ejected from the metal surface, as soon as the beam of light falls onto the surface, this is known as photoelectric effect. He also told it that if more electrons are emitted, the brightness of the light will be high. When more electrons are emitted, the brightness will be more. That means more energy is absorbed, more energy is emitted. So brightness increases. Like at present you can see it on the surface of the board. Energy is falling, it's been reflected. Energy of the light which is falling onto the particles, here the black colored components are there, they are absorbing all the lights, so they are black bodies. But the surface which is emitting the light, the white surface, it emits the light, it does not absorb, so radiations are given out, the same energy is transferred back. It is a photoelectric effect. One is a black body which absorbs or emits the light. The second one is a photoelectric effect. The same example, live example we are having it, because of the light falling on it. So radiations, at present we can say that the radiations which is not a sunlight, at present the radiation which is there is about the external source of electric current light, electricity light. You can say that it might be a tube light, right? So from that the light falls on it and it's been reflected, absorbed, emit, the shining on the surface. If more light falls at a particular surface, like you can see it in a particular surface, the more light is being emitted, because more amount of the energy is absorbed and more amount of the energy is released. So brightness of the light depends upon how much amount of the electrons are emitted back. So that is known as photoelectric effect. The another factor of it is, if I do it like this, the radiations are emitted back, but I am having a pen in my hand. Can you say that the same amount of the reflection is done by this board, the same amount of the light is reflected from the pen? No. There is a variation. That means the frequency is changed. Now in place of that, if I say that I am using the duster, it's a cloth, it's in my hand. Can you say that the same amount of the energy which is reflected by this board or by pen or by the cloth is the same? No. The minimum is there for the cloth, maximum is there for the board. So that means every component has its own minimum frequency. That is termed as threshold frequency. The minimum amount of the energy reflected, it's termed as the minimum frequency of all the objects is different. The minimum frequency is indicated, the symbol is used as nu naught. Every component has its own frequency. But when this frequency, minimum frequency, is less than actual frequency, that means I am saying it as nu naught is less than nu, or you can say that nu is greater than nu naught. In this condition, whatever the amount of the energy, that is threshold energy, is less than the actual frequency, then in that case these energies emitted or given out with a certain amount of kinetic energy, and as a result we wrote it as energy is equals to h nu according to the Planck's equation. But when you are having it as a nu naught, then in that case what will happen? That energy will be equals to h nu naught plus half mv square. You will get it as h nu naught is equals to half mv square. So giving it the equation 1 and 2 and comparing it, we get it as h nu is equals to h nu naught plus half mv square, right, under the condition when your frequency is greater than threshold frequency. So this is the one of the equation. That was again, this equation was given by Planck, this equation was given by Hertz, right? Okay, and one more change was done in these equations, that when we are doing it, it's known as photons. The package of energy, the certain package of energy which is emitted, it's known as photon, but that is for one single photon. The Einstein worked on it. Another scientist that was named as Einstein, who worked on it, and he told that for this dual nature the particle as the energy emitted by 1 mole of photon is known as 1 Einstein, right? Now he told it as energy emitted by 1 mole of photon is known as 1 Einstein. So he wrote it as 1 Einstein is equals to Ne. N is a Avogadro's number, but this is not a separate symbol, it's a single symbol, Ne. And so he made the change, E is equals to Hc by lambda. He told that Ne will be equals to NHc by lambda, where N is a Avogadro's number, 6.022 into 10 raised to 23. H, it's a Planck's constant, that is 6.626 into 10 raised to minus 34 joule. C is velocity of light, and that is 3.0 into 10 raised to 10 meter per second, right? And lambda is wavelength. Now, while doing the sum, be careful, don't cancel out these n and n. This is a one symbol, it's a single symbol Ne, it's not a multiple. So this n and this n won't be cancelled out. E is equals to Hc by lambda, value of 1 Einstein is equals to NHC by lambda. So that was the another equation which also proved it that they are particles, right? So this scientist Planck, Hertz, Einstein proved it that they are particles, right? Okay, still we are having further theories. Still we will be having it as in another factors also to prove related to these radiations having a dual nature as a wave as well as particle. But before going for it, we will be having it as in certain numericals to be done on it, right? Which are those numericals? So we will be doing it, those numericals in our next lecture, but particularly for this dual nature, which are the formulas that we will be coming across for doing it. We are having it as in frequency is equals to C by lambda, right? Actually frequency we also got it as 1 by time, right? So we got it as C by lambda frequency, so 1 by time. At the same time we get it as, this is a wave number which is equivalent to 1 by lambda. This is a one term that we will be coming across as a wave number of the waves that are passing through in a specific time period. So that we are writing it as wave number that is equals to 1 by lambda. These are all on the basis of radiations. On the basis of particles, after wave, particle, we got it as E is equals to hc by lambda. We also got it as h nu. Sorry, E is equals to h nu. So we get it as h nu. Another factor as h nu is equals to h nu naught plus half mv square, and we got it as Ne is equals to NHC by lambda. So these are the formulas. On the basis of these formulas we are going to do it, the numericals, in our next lecture, right? Within a fraction of time we'll start with our next lecture. Thank you.